Alright, let's talk about Fischer projections. Alright, now Fischer projections are a particular way of representing large, complex molecules, and we're going to see them most often used to represent structures of sugars, which we'll get to later on in the semester. Sugars you probably heard of as carbohydrates or monosaccharides, or however you have heard about them before. The fact is they all have a reasonably similar structure. They're usually comprised of about 6 carbons, alright, and this is a sugar known as D-glucose. You guys may not have heard of the D before, but we'll talk about in a bit what that is. I'm sure you guys have heard of glucose before. So sugars all exist as 2 different forms. One is the open chain form, or the straight chain form, which is shown here. They also exist in a cyclic form that we will see later on. That's not going to be a part of the video today. You can see this structure looks kind of funky and complicated. The reason for that is sugars have lots of chiral carbons. In fact, carbons 2, 3, 4, and 5 are all chiral carbons. So all sugars are overall chiral as well. So this has 4 chiral carbons. Now, this looks reasonably complex with the dashes and the wedges all going all over the place. So how about a way to draw them out that makes them look a bit easier? And that's where Fischer projections come in. So here's how to go from the actual structure to the Fischer projection. Just imagine that you are taking your hand or your foot or a brick or whatever and squash that molecule down flat. So all the dashes and all the wedges go down flat. And what you get is this result. Notice how the positions of the bonds are all the same. It's just that now you've got all straight lines and wedges and dashes. It's just easier to understand, right? These are still stereoisomers. It's just visually a little bit clearer and easier to see. Now let's talk about what this D means. D refers specifically to sugars. You can have D and L, all right? And what they are to do with is what's called the penultimate carbon. Now, penultimate is a word I learned back in England, and I've learned from people here that they apparently don't know what penultimate means. Penultimate means last but one. So the carbon that's last but one, if that's the last carbon, that's the last but one, or the penultimate carbon. Specifically, the OH on that carbon, all right? The OH is either going to be pointing to the left or to the right. In this case, it's pointed to the right, which makes it a D sugar. That's why this is D-glucose. L-glucose would be the same thing, but with the OH on the left. All right? It's only the last but one carbon, the penultimate carbon, as D and L come from. So let's talk about how can we use Fischer projections in small molecules. Well, we just do exactly the same thing. Imagine that we have a molecule here that's shown as its tetrahedral representation with 2 bonds down, 2 bonds up. All we're going to do is, again, squash it down flat and we get this. The groups are all in the same place. It's still a chiral molecule because the aldehyde, the bromine, the methyl, and the hydrogen are all the same. Are all different, I'm sorry. So that's a chiral carbon. So you could be asked, well, take this representation and convert it to Fischer. Well, this is the Fischer projection. What if you're asked, well, go from the Fischer projection to the normal representation? Well, this is the way to do it. You can go this way or this way. So what if we do an application of them? The question is, draw the Fischer projections for the D and L stereoisomers, in other words, 2, so there's 2 of them, of 2-hydroxypropanol, and then label these as D or L. So the only thing that's new here is the term hydroxy. Hydroxy is the term for OH as a substituent. All right. So propanol is 3 carbons. The al means aldehyde. The 2 means the hydroxy, or the alcohol is on carbon 2. Now, I've drawn this 3 different ways. All these are 2-hydroxypropanol. All right. This is the skeletal form. This is the skeletal form with the aldehyde shortcut. And that CHO is a shortcut way of writing out this. If you prefer, we have the expanded form here, but all 3 of them are 2-hydroxypropanol. So for the Fischer projection, the thing we have to make sure is that we draw the carbons pointing up and down with the aldehyde up at the top. So here's what we're going to do. We can actually take this molecule and actually just turn it around 90 degrees. So we get the CHO, or the aldehyde, or whatever you want to call it, up at the top. And then we draw a straight line down. Here we have the CH3, and that's going to go on the bottom. And in the middle is going to be our, one's a bit long there, is our middle carbon. Alright? That has the H and the OH on it. Now, you can't necessarily tell from here where you should put the H and OH. Well, that's why it says D and L stereoisomers, because you're going to draw out two. So let's draw out them both. Let's put the CH3 at the bottom again. Now, from what we said before, when we have the OH group on the right, that's the D stereoisomer. And then when we have the OH on the left, that's the L stereoisomer. In other words, this would be D, 2-hydroxypropanol. This would be L, 2-hydroxypropanol. And that's how it works.